Hello students, I am Dr. Tautomerism. I welcome you all in my channel Chemistry, the Mystery of Molecules. Today's topic of discussion is one very interesting topic, that is preparation of 1,2-dicarbonyl compounds from carbonyl or alpha-hydroxy carbonyl, etc. I mean derivative of carbonyl you may consider. Now for that purpose we will discuss four methods. One is nitrosation followed by oxidation. Second method is selenium dioxide oxidation of carbonyl. The third method is oxidation of alpha-hydroxy carbonyl, and the final or fourth method is oxidation of 1,2-diol. So this video is going to be pretty interesting. Let's start. So before going to details, one MCQ question is, what is the major product of these reaction? It's a very easy question, student. This is actually alpha-hydroxy carbonyl compound, and if you treat it with copper acetate, what is the major product? Here four options are provided and one of them is the right answer. I request you student, please pause the video, try by yourself, and whatever answer you get, please write in the comment box along with few words as explanation. Don't hesitate, because your answer, because whatever you do is right or wrong, it doesn't matter, and after some time you'll get the right answer with proper explanation. So let's go to the main topic, the first method. The first method is by Nitroso-Oxime tautomerism. So from, you may consider from ketone we will prepare, this is 1,2-diketone. Why 1,2? Because these two are adjacent together. Okay, so how this conversion could be achieved, or how this 1,2-diketone could be prepared? The reagent is NaMnO2 dilute HCl in ethanol. Student, these reagent have a pretty similarity with diazonium salt preparation, not ethanol. In that case we have used water and 0 to 5 degrees centigrade, but here the reaction is somehow similar, because in presence of this NaNO2 dilute HCl, it produces HNO2. And these nitrogen, obviously one has lone pair, and in the next step these HNO2, this nitrous acid is get protonated and it forms OH2 plus. This is a cation, and because of this H2O means OH2 plus formation, this part, student, it's become a very good leaving group, because the after leaving the molecule is actually water. It's a neutral molecule, neutral leaving group, and consequently what it produces? It produces N double bond O, and obviously the positive charge is on nitrogen, and this is, student, the electrophile. Okay, so in the next step, actually for diazotization also same, this NO plus is the electrophile, but from here the reaction course will follow a different pathway. Now the first step of this is, actually if I want to discuss the mechanism, the first step is Nitroso-Oxime tautomerism. So if you look at this carbonyl, or this is actually ketone, so it has a CH2 group. In presence of acid, it can undergo keto-to-enol conversion. Actually this is keto-enol tautomerism, and by the way, student, I have discussed previously a dedicated lecture on this topic. Please visit for better understanding. Now this is enol. Since I have used acid, so that's why it is enol. If I have used base, then it will be corresponding anion or enolate. Now in the next page, what you can expect, that these enol can undergo nucleophilic, means it will act as nucleophile and it will attack these electrophile, which is produced through reaction between these NaNO2 and dilute HCl. This is the electrophile NO plus. So obviously you can think that these lone pair will be pushed here and it will attack through the carbon, because carbon center is more nucleophilic. That's why attack will happen from this carbon center, and it will produce this alpha nitroso, because this group in organic chemistry, student, we call it nitroso. So if I write more accurately, I should say that this is. So if you look at this nitroso compound, so the relationship between this carbon and nitrogen is 1,3 type. I mean that 1,3-dicarbonyl or active methylene type. I have already discussed many lectures on such molecules. Now these molecules have a very unique character. What is this? these two protons are significantly acidic because the corresponding carbanion, if it leaves, or the conjugate base is resonance stabilized by one way this and another. So you may consider it's a doubly stabilized. So similar thing is possible for this compound also, this alpha nitroso-ketone, and this proton is involved in this process. So what can happen? This could be released easily, and not only that, if your medium is acidic, then it can undergo enolization. Similarly, if I say that student, if you look at this 1,3-dicarbonyl compound, they can also undergo enol formation very much easily. Why? Because of the stability of enol. So this is the OH and double bond, and another carbonyl is intact, and these enol is resonance stabilized by these hydrogen bonding. So this is hydrogen bonding. So similar story you can expect for these molecule also. So in acidic medium it will preferentially undergo this enol formation. Okay, now actually I have written this is a trans type conformation. If you want, then for you I can write the cis type orientation too. So you can expect that, okay, this is enol, so this side OH, this side N double bond O, OH, this one thing possible, this is R1, R1, R2. Along with that there is another form possible. What? This is R1, C double bond O, this is C double bond, sorry, N, this is O, this is H. So it can further be stabilized too. Okay, so this is the example how this compound could be stabilized through hydrogen bonding. I mean, this is the hydrogen bond. Now, so this part we have understand. Now the question is, what will happen in the next? Student, after this enolization, one thing may be clear to you. What do I mean? So if you look at little more carefully, that this part is nothing but C base, or you can consider it as imine, or in this particular molecule you can consider it as oxime. Okay, it's a C base between carbonyl and hydroxylamine, which is called as oxime. By the way, I have already discussed a dedicated lecture on ship base. Please visit if you have any doubt. Now, so from this we can understand we have prepared the C base or imine or oxime because of this Nitroso-Oxime tautomerization. So this step is, student, this step is called Nitroso-Oxime tautomerism. The first step was Keto-enol tautomerism. Second step, so let me write it here. Step 1 is Keto-enol, and the step 2, this is Nitroso-Oxime tautomerism. Okay, now this we get fine. In the next phase, it is treated with a dilute acid or dilute aqueous acid, and we know that these C base or imines are not stable in aqueous acidic condition. Consequently, they undergo hydrolysis of this imine bond, and it produces, one side is carbonyl, another side means this double bond will only hydrolyze, and another side it will produce hydroxyl amine derivative. But student, this molecule will not remain at hydroxylamine, it will be protonated instantly because medium is acidic, and these hydroxyl amines are significantly basic because of adjacent lone pair repulsion or alpha effect. Means these two nitrogen repels together. Okay, so this is called alpha effect. So because of this, directly from monoketone to diketone will be produced. Now apparently if you look at it, it will look like, sir, this is nothing but oxidation reaction. This is oxidation reaction. So this part, this ketone is oxidized to diketone. So who is reduced? Student, imine. Sorry, this is nitro. So actually the previous compound was HNO2, nitrous acid, and after this it's converted into hydroxyl amine. So from here you can clearly look at, this is nothing but reduction reaction. So this is the overall redox story. Now Next, let's go to the second method. Second method is relay oxidation by selenium dioxide. Selenium dioxide is actually a oxidizing agent, and here the oxidation state of this selenium atom is +4. So it reacts with aldehyde or ketone, anything, where it is necessary that alpha carbon should have at least 2 hydrogen. So 2 alpha hydrogens are needed, and upon oxidation it's converted into 1,2-dicarbonyl compound, and this reaction is carried out in acidic medium. So you can see 3 examples. First example is this is acetaldehyde produces glyoxal. In this case this is phenyl methyl ketone, and here upon selenium dioxide oxidation it produces, this is phenyl glyoxal. Here interesting point, this phenyl side is not oxidized because it do not have 2 alpha hydrogen. So this methyl group is oxidized to the corresponding carbonyl. The third example, this is a cyclopentanone cyclic ketone, which similarly undergoes oxidation by this selenium dioxide in acidic medium, produces the cyclopentadione. By the way student, this molecule, if you look at the other molecules and this molecule, it's a very interesting. Why? All other molecules, all others, these aliphatic or acyclics are trans type, because in this way they can avoid the dipolar repulsion, because another thing, adjacent 2 carbon containing this double bond O is not that much stable, very much electron deficient. So they orient themselves in this way such that the polarity could be minimized or dipolar repulsion could be minimized. But these molecules do not have any option. Why? Because of its rigid structure or cyclic structure. Because ring, in case of ring, CC rotation not possible, but here CC rotation possible. So that's why these 2 dipoles are this side same. So consequently this molecule have a neat dipole moment, and this is relatively more reactive compared to their acyclic counterpart. So remember, this is the important question too. Okay, so let's go to our main topic, how this reaction happens or mechanism. So this relay oxidation mechanism is explained here. So first, similarly keto-enol tautomerism happens in presence of acid. Recall student, we have taken dilute acetic acid, which is weak acid. So this acidic medium, and it undergo enolization. Through similar way it reacts with selenium dioxide. And for your better understanding, you may think that this selenium atom attached to 2 oxygen with double bonds, and oxygen is more electronegative compared to selenium. So you can consider this selenium center is carrying delta positive charge. It means it is electrophilic. This much is enough for us. And we know the alpha carbon of this enol, or actually enol carbon means double bond attached carbon, where this double bond is attached to the sp2 carbon, is actually nucleophilic in nature. And similar way, just I have shown previously, so it will push, it will attack, it will open. So in this way this moiety will be produced. Selenium at carbon, selenium bond formation, and selenium is attached with this ketone. Now if you look at student, these molecules also have 1,3-dicarbonyl type, similar. So this proton is significantly acidic. Not only that, since medium is weakly acidic, so we will not go that point. We will think from enolization point of view. Okay, so you may consider that, sir, this proton will be consumed and it will form OH. Okay, so this is, but later on these from 2 OH or gem-diol type, 1 water molecule will be eliminated. You may consider this way, 1 water will be eliminated and it will produce carbon double bond selenium and selenium double bond oxygen. By the way, if you have any query that, sir, it should not be linear like this, no student, because this selenium still has 1 lone pair of electrons, so it's a trigonal type. So now these we understand, it's a double bond formation. Fine. In the next step, similar way like that imine hydrolysis will happen. You can think that, sir, water will come and it will attack here, it will open up, it will produce these intermediate. Later on you can expect that these lone pair will push and the selenium will go. So that's another thing you may think, but I suggest you student, don't need to go so much complication. Instead of that, just remember one thing, that water will break it, oxygen part of water will go to these carbon, means carbonyl group will be produced, and these two hydrogens will come with this selenium. So we will not focus on the fate of selenium, just fate of the product. So you can see this CH2 part is actually oxidized into C double bond O, this red color. So this is actually the oxidizing agent, this is the oxidation. And what is the, means who undergo reduction? The selenium dioxide. Actually at the beginning I told the selenium is in +4 oxidation state, so it is oxidizing in nature. So this is the second method by which these carbonyl to 1,2-dicarbonyl conversion could be achieved efficiently. Now let's go to the third method, that is 1,2-diketone preparation from alpha-hydroxy carbonyl. It's very interesting, but a simple question comes, sir, it is not a well-known compound, alpha-hydroxy compound, how it could be prepared? I guess student, you both know this. First reaction, if you want to prepare this from A star, it has a name, it's a name reaction, acylone ester condensation. I guess you know it. I have already discussed many lectures on this. So this is one method. Second method, if you want to prepare from aldehyde, means for example if you take aromatic aldehyde or like that, you can prepare these via benzoin condensation. This is a very famous name reaction. Okay, so and here concept of umpolong is associated with. So in this way we can prepare this alpha-hydroxy carbonyl compound. Now these alpha-hydroxy carbonyl compound, if you treat with copper 2 acetate, I repeat student, remember the oxidation state, copper 2 acetate in presence of acetic acid, it produces 1,2-diketone, and this mechanism is nothing but via single electron transfer. Single electron transfer pathway, it is oxidized. And you may think, actually I am not saying this is a way, so you may think that one electron is first taken from this oxygen, its radical cation, then this proton is released and ultimately it converted into 1,2-diketo derivative. By the way, what is the fate of this copper? You can copper 1. It's a very interesting thing, and I think now student you got the answer of the MCQ. Okay, this is one of the method. Now let's go to the last method. Actually this is the least famous method you may consider, that is oxidation of 1,2-diol to the corresponding 1,2-diketo compound. Now if you look at this, this is actually 1,2-diols. By the way, I have taken this thing from the reference European Patent Office, this is the patent number. So here 1,2-diol, so all are 1,2-diol or glycol. So if you oxidize them in presence of IBX, so this is a hypervalent iodine reagent, you can see this iodine center, this is in high oxidation state. Generally halogen prefers to remain in -1 oxidation state, but because of the larger size and least electronegativity, this iodine could be oxidized very easily to higher valent oxidation state, and this is actually a very selective reagent, this IBX. So in presence of 2.5 equivalent IBX, these glycols or 1,2-diols could be oxidized selectively. See 100% yield to corresponding dimethyl glyoxal. This molecule name is dimethyl glyoxal, or butane 2,4-dione, you may say that too also. Even these cyclohexane diol, cis or trans, both type, or syn or anti, that type, since no double bond is here, so it will convert it into this diketone with 81% yield and 78% yield. And see the time student, 3 hours, 3 to 5 or 5 hours. It's a very selective reaction, but very less example I found. So this is the fourth example for conversion or preparation of 1,2-dicarbonyl compounds. Now let's come back to our MCQ. So as I told, it is a single electron oxidation, and this copper 2 is oxidizing agent. It oxidizes these alpha-hydroxy compound into corresponding dicarbonyl. So this is the answer. And by the way, how can you prepare this student? This you can prepare very easily from benzaldehyde and alkali. Okay, even potassium cyanide, means alkaline potassium cyanide, if you treat it through benzoin condensation, it will produce this this is alpha-hydroxy ketone, or it has a name called benzoin. And this molecule, the product has another name, benzyl, and this is used for the another name reaction, benzylic acid rearrangement. I have already discussed that too. Now, so if you don't know this answer, how can you come up to the right answer in less than 30 seconds? Student, this is actually an oxidizing agent, and copper 2 is actually a mild oxidizing agent. So where oxidation can happen? Obviously this, okay, because ketone oxidation to acid means if you want to oxidize the ketone further, you have to break this carbon-carbon bond. Those are pretty difficult. That's why we have learned that oxidation of secondary alcohol to ketone is easier, but further oxidation of ketone is difficult because it is associated with CC bond rupture, and CC bond is significantly stable, so this pathway is not that much preferred compared to other oxidation like this oxygen to carbonyl is there, and one of the option is also given this, so this is possible. Second, if you do a back calculation, I mean that if you look at the options from these benzaldehyde, this is a reduction, student. So if copper does this, copper will convert into copper 3 or 4, which is not usual. So this is not a usual option, so it's gone. If you look at same, this is also a reduction because I had a hydroxyl, so some 2-unit reduction is needed, so even that is not possible. If you look at the second option A, it is also reduction because carbonyl got reduced into diol. So fourth option. So if you don't know actually the answer, if you have common sense as what type of reagent and what oxidation state copper may have easily, so from that you can come to the right answer. Okay, so this is the end of this main discussion. Now let's see what we have learned. So in conclusion, we have learned that 1,2-dicarbonyl compounds could easily be prepared by nitrosation followed by oxidation, selenium dioxide oxidation, oxidation of alpha-hydroxy carbonyl, or oxidation of 1,2-diol or their derivatives. And these dicarbonyl compounds are very good electrophilic reagent. They are more reactive than single carbonyl due to their electron withdrawing nature. I mean, just look at two carbonyl group. Those two carbonyl group are adjacent, and the same carbon, both carbon and sp2 hybridized adjacent. So that's why once electron deficiency or one will insert -I effect on another, and consequently they will be more reactive. Not only that, the LUMO can overlap together and reproduce a less energy LUMO, means further less energy LUMO, which can accept electron density more easily. So they are very good electrophile, student. Electron deficient, so nucleophile can attack one of the carbonyl carbon very easily. Now next point is the ketones display electrophilicity through the carbonyl carbon, and ketone shows nucleophilicity by enol or enolate formation. If you take the acidic medium, it will produce the enol. If you take basic medium, it will produce enolate. But in this way, the alpha carbon of the carbonyl group shows its nucleophilicity. But actually, I think it is depending on the pH of the medium. You may consider like that. And final method, this benzoin or acylone could easily be oxidized to copper 2 complex, nitric acid, or iron 3 means ferric chloride reagents. So this is the overall discussion. I believe this video will be useful. If you really enjoy the content of my channel, please help this channel to grow by subscribe this video, like this video, and share among your friends, and write your opinion in the comment box. I have seen many people watches my video but they don't do subscribe. Please do it, it motivates a lot. And if you want to know further, you may visit 2 of my other channel. So stay happy, stay blessed. See you in my next video. Bye bye.